Hello and welcome back to Impact Quantum, and your ears do not deceive you. I am not Bailey. Bailey is on holiday because, yes, even AI agents need to take a break. Now, in this episode, we get into some very interesting discussions around quantum chemistry and its implications for medicine, science, and, well, just about everything. So, I also get to geek out because at one point in the past, I was a chemical engineering major. So, brought back a lot of memories. So here's the show. And no dubstep this time. Hello, and welcome back to Impact Quantum, the podcast. We explore the emerging field of quantum computing, where you don't need to be a PhD in physics, but it probably helps. You just need to be a little curious, right? And the most quantum curious person I know, and maybe even the most curious person I know, is with me, Candice Gahuli. How's it going, Candice?
It's great. Thank you so much. The sky is blue, the sun is shining. It's just going to be a beautiful day today. I'm very excited.
Nice, nice. We're recording this as I'm on the West Coast for Microsoft Ignite, and it is. I can smell the fresh Pacific air, and it's about 20 degrees warmer than it is at home. So all the locals are saying how cold it is, but I'm loving it.
You see, it's all depends on where you come from, right?
It's all
It's
relative.
exactly. So
Uh,
today we are lucky enough to be speaking with Natasha Nadoveza. I definitely mispronounced the last name. I apologize. And she is involved in nuclear quantum dynamics. Hi, Natasha. How are you today?
Hi, I'm really good. Thank you for inviting me.
cool. So the obvious question is, what exactly is computational and quantum chemistry? And what does nuclear physics have to do with it? Because most people, I think I know the answer, but most people, when they think of nuclear physics, they think, nuclear reactors, nuclear weapons, that sort of thing.
Yeah. Well, I mean, that's also what is nuclear physics. But in this
Right.
case, with nuclear quantum dynamics, we usually refer to, well, first, quantum dynamics. It's basically the study of systems which evolve in time, ergo dynamics, following the quantum laws. So basically, we are solving the equations of motions which are derived from quantum dynamics, from quantum mechanics. And the nuclear is just to say that we are following, in this case, the motion of nuclei. So in my particular project, we are working on studying chemical reactivity. So we are studying how the bond in a molecule will break, but we are following the motion during this process of the nuclei.
Interesting. And can those be used to do computations?
Well, I mean, in this case, we are using still the classical computers to do quantum dynamics. Whether or not it can be done on the quantum computers, if that is your question, that is probably one of the most promising applications, but I don't really know much about that particular field. So it is, as far as I know, it is still under the development.
That's cool.
When we were preparing for the call, you had mentioned to me that you had recently completed your PhD work. Congratulations on that. That's a very big deal.
Yes.
I'm very curious, at what moment early in your, I want to say in your education, once you hit university, like at what moment did you realize that this was the field that you wanted to commit yourself to?
Well, I guess that was at the end of my master's studies, because in principle, I have a background in chemistry. So I was always interested in how we can understand the world around us at the molecular level. I kind of very naively thought back then that we can understand everything if we understand the behavior of molecules. Now, it's not really everything, but it is still quite a lot. And as I had a background in experimental chemistry, in principle, a lot of organic chemistry, biochemistry, synthesis, and analysis, when I first started learning about the quantum mechanics, which was quite late in my studies, when I got into this field, I realized that in principle, if we can do this kind of calculations, we can follow the behavior of molecules and its very nature and its very core. And that was kind of like the more underlying level of, if we understand how this very basic behavior influences the molecules, and we can understand how the molecules influence much more bigger processes, and then we kind of can do this stepwise understanding of different phenomena. And that's when I got interested into this particular field of quantum dynamics. And
Interesting.
Yeah.
Well, you work at the intersection of this deep theoretical chemistry, and I want to think about real world applications. What do you think is the biggest challenge in translating quantum level simulations into deployable industrial tools?
Well, the thing is that I would say the biggest challenge that we are facing is the size of the system which we can study at this level of theory. In my particular case, I was working in a very small molecule, methane, which is basically the smallest possible carbohydrate that you can have. And we were studying the breakage of a CH bond in that molecule. And even when you have a very, very small system, it can get very computationally difficult because there is a lot of parameters to take into account if you want to have this very high level of theory. And on the one hand, there is importance because if we can understand on such level how the energy is flowing through the system, how the energy is actually being used, then it can have a very important industrial application because this particular reaction is still the main route to produce hydrogen. And then if we could understand better how to control this process with much smaller input of energy and the much smaller cost of the process, we could actually have much bigger gain. But the problem is, in order to understand this on such a high level of theory, we can work on a very small system, because if we would want to increase the size of the system, if we would want to, let's say, if we have a metal as a catalyst, it also affects the process. But if we would want to take into account also movement of these atoms, the system would grow exponentially and it wouldn't really be doable anymore. So there is always this balance in between how accurate answer we want and how big of a question we can ask to get that accuracy.
And that has been, you know, like what they say is classically intractable problems in computer science, right? And this is the idea that quantum computers are able to address those problems more effectively. Not all problems, but just some problems.
Mm-hmm.
Unfortunately, some of those problems are really important. Whether it's chemistry, kind of everything we experience in life has something to do with chemistry, right? Ourselves has to do with chemistry. What do what is the potential here for drug discovery and like side effect mitigation and things like that? Like, is that one of the top um, advantages of this technology? You could simulate that?
Well, in principle, I would say if you talk about the accuracy, then also we need to take into account, as I mentioned, the size of the system, because if the system is quite big, then these quantum effects might not play such a significant role. So when it comes to drug discovery, if you're talking about the molecular processes, when we have, for example, let's say we have this specific part of the enzyme, which I'm pretty sure your future guest will explain much better. But if we have something which can be, let's say, presented with on a much smaller scale, then these effects might be much more relevant, obviously. But if you say, if you talk about as you mentioned, the side effects of the drugs. Now, if we talk about, I would say, again, it's not really my field, but I would imagine that the side effect might have to react on a much bigger scale, because side effect would be, we don't really know where it will be. It could be affecting some of different organs. So then we would need to take human organism as a bigger, let's say, the whole, and then probably we wouldn't have so emphasized molecular effects. But still, these kind of simulations, I think, could be still improved by the quantum computing, because it doesn't necessarily need to be on the molecular level. It can also be for different kinds of simulations can be sped up. And different kinds of simulations have different problems in terms of computational efficiency.
Interesting.
So if you could, pick a problem, what is there like an unsolved problem that keeps you up at night where you say, I really hope one day to explore or help answer? Is there any type of problem like that you could mention?
Well, one of the things that I find very interesting is that usually when we talk about quantum dynamics, we either study the movement of electrons or as a chemist in chemistry, or the movement of nuclei. But what I think it would be very interesting if we could study, let's say, the chemical reactivity by following all of those elements, if they would all move at the same time. Now, this is something which is computationally very difficult, and I don't know if there is any potential of it actually being possible anytime soon. But I feel like if that would be possible, it would be really amazing, because then we could gain much better insight into, for example, chemical reactivity or molecular behavior on a much more accurate way.
Interesting. But it's not just medicine, right? I mean, we could create better fuels, better batteries, right? There's all sorts of potential here. Does any one of those in particular interest you?
Well, I would say I'm the most interested in biological or medical applications, but as you mentioned, like in principle, most of the things are in the end chemical. For example, if we want to talk about reducing the CO emission, then as far as I know, there's a lot of research where how this can be captured or converted into something, or how the fuels are going to be burned, or a lot of those processes in the end, or a lot of catalysis and a lot of different reactions in photovoltaics, and a lot of processes are actually depending on the chemistry.
So you mentioned catalytic and catalysis, which oddly enough, that's a harder word. Catalytic is easier to say. I actually, fun fact, started my college career to be a chemical engineer, but I switched to computer science. And I think I remember, but could you explain what catalytic processes are for those who are not chemistry aware? Not that I'm chemistry aware. I hear the terms and I'm like, oh, I remember that talk. Yeah, I remember that. So what exactly is catalytic?
Well, in principle, in chemistry, when you have a chemical reaction, it will involve, let's say, the breakage of a certain bond. Now, in order to break a bond, you have an energy of activation. You need to give some energy to the system in order for this bond to be broken. Now, the catalytic process is usually some third party, let's say, which is participating in this chemical reaction, and it just serves to reduce this energy barrier. So it's, in this sense, helping the chemical reaction in the sense that you don't need to put that much of energy to break, let's say, a bond, but this activation will be much lower. And a lot of processes that are important could be quite expensive without a catalyst, or even not possible, which is why there is always a need to investigate which kind of material will be most efficient in this.
Yeah, that makes sense. Most people, I think, know that word catalytic from their cars and catalytic converters.
I'm not really sure what it is.
Oh, it's something that they put on. I don't know exactly what it does, but it meant to clean the emissions, and it's basically when the exhaust pipe goes through the muffler to reduce the sound, but it also goes to something called like a catalytic converter to scrub some of the particles from it or break down some of the bonds, so the emission's not as toxic. I'm sure someone will tell us in the comments, Candace, exactly what a catalytic converter does. But yeah.
I had mine stolen off my car when I was.
And they tend to get stolen a lot because I think historically they use platinum in them. So they were inherently expensive. They used to be like a couple of thousands of dollars to fix or replace. But I think they've changed the formula. So if you get it on newer cars, they're not made of as expensive material, and as a result, the thefts are not as important. So typically, yeah, but I think about 5-10 years old cars would start having the platinum in them.
There you go. So we've talked a lot about chemical reactions. We've talked about enzymes. I'm wondering if you could explain just at the very basic level, what happens during a chemical reaction to someone who's never taken any chemistry and doesn't really understand it. How can you describe it?
Okay, well, the first thing that one needs to understand is that there is a molecule, right? And the molecule contains different atoms, and these atoms are bonded in a certain way. Now, the chemical reaction in principle means that some of these bonds will be broken and some new bonds might be created. So the structure of the molecule itself will change. That's let's say, in the most basic way.
That's fair. So let me ask you, what are you looking for what does quantum mean in the context of chemistry? Are you like expecting like molecules to be dancing around or interacting? Like, what are you looking for when you're running these kind of simulations?
Well, it depends on the kind of simulation. If we are looking at this, for example, what I was working on with the chemical reactivity, what we have there is that we wanted to study what is the probability of a bond being broken. Now, there is a lot of experiments that are done, and now the experiments are getting very advanced. One can prepare actually a quite precise quantum state of a molecule. Now, the quantum state, as you said, the molecule, if in this case, if we consider it as a single molecule, which probably not going to be single, but all of the bonds are vibrating. The molecule is also rotating a bit, as you said. It's like dancing around. And then if they are all dancing with the same energy in the same way, we say it's the same quantum state. And then
okay.
you
Sorry, go ahead.
can no, go ahead if you
I
had
had
a
a light
question.
bulb moment, so like I.
Okay.
It's good. It's good. It's good,
So-
right? Things are making sense, you know?
Yeah. So the experiment would be depending on what kind of quantum state we prepare, how is the chemical reaction going to go? What is the goal is always, if we want bonds to break, then the goal is to prepare such a state so that the probability of bond breaking is the highest possible, right? So in this sense, when we do this simulation, that is exactly kind of what we do. We try to follow the evolution of a molecule of a specific state, and in the theory we can prepare this specific state much easier than experiment, because in experiment you have a lot of molecules, and then there is a quite complicated apparatus to prepare it in a quite uniform state. And it's not going to be exactly uniform, but if there could be as close as possible, then experiment is more precise. But in theory we can much easier than use one single state and just see how the molecule will evolve going from there. So now I kind of forgot what was your question, but the point of the simulation in this sense would be to see what are the different effects that are affecting the probability of this bond being broken. And the reason why we need quantum effects here, it's not only necessarily that there might be some quantum effect. No, the most famous one is tunneling. And of course, when you're breaking a CH bond where you have a hydrogen and carbon, the hydrogen is quite small, it's quite light, and it can have the tunneling, meaning that, as I mentioned earlier, there is this activation energy, and this molecule, this atom doesn't really need to go through this whole barrier. It can tunnel through it, so the reaction can happen at the lower energy than it would, which is one of the quantum effects. But
Which
this
could
is
save
not,
a lot of money in energy consumption if you figured out how those tunneling effects work. Okay, that makes sense to me now. Sorry, I
Yeah,
cut you
but
off again.
no,
This
I
is
just
great,
wanted to
Candace. I
say,
had
Two light bulb moments.
two light bulb moments after a very long, exhausting week. That's good. My brain
It's-
does still work.
There, yeah.
okay, so what I wanted to say, it's not only about the quantum effect, it's also that if we want to understand, even without the quantum effects, even without the tunneling, if we want to understand how exactly this process is going, it's much better if we could study it, if we could apply the mathematical equations, the models that actually correspond to the nature of our system, which is why we do quantum dynamics in this case. Because the way the atoms are behaving and the molecules, they're following this, they're not following the classical laws of physics.
Okay, and to that point, what's something surprising that you've learned about how the molecules behave that most people would never guess?
Most surprising way. Well, I would say one of the surprising way is that the way the molecules use the energy, because I think that's I think that's what surprises the people is that the levels are quantized, which means that the molecule cannot be in. If we talk, for example, about the vibration of a bond, right? So if we have, let's say, I have two balls and they are vibrating, they could be vibrating in any different way. But if you go to the quantum level, then not every state is, let's say, possible because the states are quantized. So it can be in one quantum state or it can be in another. But what is in between is just there isn't a state in between.
It's kind of
Oh.
like I remember learning this when I was a young lad, or at least a younger lad, that it's kind of like steps and stairs, right?
Mm-hmm.
You really can't be in between the steps, right? You
Yeah.
can't stand in between the steps, right? You can, so that analogy works better, right? So
Kind
so
of,
all
yeah.
those states in between the individual, I think electrons. I don't know if it applies to other particles too, can only be in certain orbits in certain places. So that is one of the, for me, I thought was one of the great mysteries. Like, well, you know, in our physical world, right? Like, you know, when I'm going up the stairs, I exist at some point on every level there. But at the quantum level, it almost like, for lack of a better term, pixelates, you know?
Yeah, that's what people say, that the levels and the general states, they're like quantized. So there are specific, I mean, there are states, but they aren't continuous.
And that blew my mind when I heard that. Still does.
Oh, this stuff is so fascinating to me. What do you think people misunderstand most about chemical reactions, how they actually work in nature?
Hmm. Well, I'm not quite sure if people actually think about chemical reactions unless they really need to.
Okay,
But
Fair
so
enough.
it's I haven't encountered many misconceptions. So I don't know. Maybe you can tell me what you think about chemical reaction, and I can tell you if it's a misconception or not.
well, we keep on going
Or it,
back to photosynthesis, and
Yeah.
quantum tunneling, and that is just not something I ever thought about. Photosynthesis as something that was quantum. But then how, you know, the light is reacting and the changing of the molecules and creating these chemical reactions. I found that to be incredibly fascinating. It's not something I saw in the first place as that. So um, that was something that had surprised me.
And the other thing
Uh,
too that I really respect about plants, which sounds like a weird statement, is the fact that they are little, every leaf is a little solar panel, but they've also figured out the energy storage mechanism, right?
Mhm.
So they store it basically as sugars or some kind of sugar, right? And that can be, you know, metabolized later or burned later, depending on what words you want to use. I think that's amazing because the biggest problem, I think, with solar panel or renewables today is the energy storage. Um, and, you know, right now, I think most people think of those as separate things, solar panels, right? You can slap a solar panel on anything, but you don't get the most use out of it unless you find a way to store that energy.
Mm-hmm.
And pushing that energy into the grid has a lot of other logistical problems for the power company. So it's not, I think if I had to answer the question, what is the most common misconception? It's people don't understand that these things are complicated, right? These things have
Mm-hmm.
connections, right? So most people, you know, will say, well, we'll just put solar panels in everything. Well, that's great, but when the sun is out, you're generating a lot of power, and that disrupts kind of how the grid can kind of adjust the power levels and things like that. So it's not as simple
Mm-hmm.
as just slap on a solar panel, right? You have to find a way to store that energy for later. Plus, the sun never shines at night, right? So unless you're in the North
Yeah.
Pole or South Pole, but you know, for the most part, I think people don't understand. I think it kind of is like kind of what you said, right? People don't think about this, right? And chemistry is literally involved in everything we do.
Mm-hmm. Yeah. Well, in principle, a lot of this research in, like, let's say, this artificial photosynthesis or solar panels is actually inspired by nature, because you said nature usually figures the most elegant way to do, well, basically everything that we could
Right.
possibly think of. So the only matter is trying to understand how it actually works in nature, how the nature regulated and solve these issues, and then to try to somehow recreate our own solution and to try to adapt it to what we need to do it for.
It's interesting. Where do you think quantum effects matter most in our real lives? Is it in our bodies, in materials, in energy, or something else? What do you think?
Yeah, that's the question I get a lot when I tell people what I'm working on, because my thesis was about the quantum effects in this, and then people are like, "But what are quantum effects?" And like, are they any relevant? Because usually people think about the quantum, they think about the very, let's say, electrons and atoms, and that doesn't seem to be very relevant to the world we are living in, because it's just so much smaller and we cannot really see, we cannot interact with it. But I would say, in principle, they could play probably a very significant role in a lot of processes. If we go to elementary level, like for example, the way we see things, or the way our senses work, or well, in principle, chemical reactions is, let's say, probably the most obvious one. But a lot of those things, even though they're on the very, let's say, small level, they could still have effect on the much bigger scale.
Okay. So can you explain to me why can quantum chemistry explain and help me understand why certain reactions happen quickly while others barely happen at all?
Oh, well, probably. I mean, it's kind of, well, actually, with the quantum chemistry, people usually refer to, let's say, calculating electronic structure, which is basically calculating the energy of a given structure of a molecule. So I don't know if that first, if there is an approach that would be applied directly to reactivity. But this is extremely important because if you want to understand how, usually in chemical reaction, as you mentioned, whether it will happen or not, it can depend on many different things. But the main things are depending on the energy. How does the energy flow? How does the energy change if you're going from one state to another? And then if you want to understand how these things are happening, then you would have to know exactly at this state what exactly is the energy, because sometimes differences could be not that big. And especially if you have different competing reactions. For example, if you have a lot of different processes that could go at the same time, then the question is, well, which one will go faster and which one will be energetically more favorable. So for all of those questions, one would need to have a quite precise calculations, and that's where the quantum chemistry can play a role.
Interesting. What is an enzyme? Because
Enzyme.
I remember the answer, and there were things that always bothered me, like about how they work. But what is an enzyme basically?
I mean, as much as I probably remember as much as you do from the
No,
biology
no, I'm
classes,
sure you remember
I
more.
always, as far as I remember, enzyme is in principle in biology doing what the catalyst is doing in, well, chemical reactions which are not biological. So it is helping chemical reactions. It is kind of
But they don't
participating.
participate in the reactions too, right? That was the thing that blew my mind. Like that's what I
That's
remember that blew my mind was like, well, they're involved, they make things easier, they lower the energy state. Again, I guess going back to what you said, right? Nature always finds out a pretty elegant way, right?
mm-hmm.
My favorite line from Jurassic Park, the original was "Life finds a way," right? Um, no, like, and that blew my mind because it seems like it almost seemed, and I know it doesn't because it can't. Like, it almost seems like it violates the like thermodynamics because it's like it lowers the energy state, doesn't participate. I don't know. That's the part that always blew my mind, right? Like, I don't want to go down too far
Well,
down this rabbit hole, but
I
I don't talk to chemistry PhDs very often, so like I always, and there was a previous show we had where I was like, lasers were finally explained in a reasonable way, and I was so excited about that. Like, but anyway.
So
yeah.
how does quantum chemistry change your understanding of everyday things in life, like color, smell, light?
Well, I mean, quantum chemistry is a very
Yes.
broad field, so it can be applied to different, let's say, aspects of our life. But I don't know if we could, if it's enough to use only quantum chemistry and to use only that kind of study to change the things that you mentioned about the smell or how the baby see. I think there's much more processes involved there, and I would say it does a certain contribution, but I don't think that it actually it provides the full answer to something, so big as such a about the questions which depend on so many different processes.
Fascinating. All this is just fascinating, right? I mean, like, people think science is boring. A lot of people, not all people. No one on this call, obviously.
Right.
But like it's just so fascinating. Like, there's just so much to it that can explain so many things. The thing that when I was a kid I learned that just blew my mind was things that are good heat insulators tend to be good electrical insulators. And things that are conduct heat pretty well tend to be very good electrical conductors too, right? Like So the idea that glass can kind of, be like doesn't transfer temperature very easily, but metal does, right? So, I don't know. For me, like that was the thing that was like, well, why is that? Like, and you start pulling at the threads and you start pulling at the threads and ultimately you get down to the molecular level of like why that is, right? And I guess, now you can go down to the submolecular level of like, well, why is that? Right? It's just one of those things where, um, yeah, I'm like, it's a cool field. Like it's not for the timid, that's for sure, because there's a lot of everything. There's a lot of math. There's a lot of rules to memorize. But there's a lot to it. But like, I feel like once you kind of get a sense of like, um, chemistry, you can understand a lot more things. Like it's kind of like it really is at that bridge of it's like a junction box, so to speak, right? Of physics, biology, and yeah, I guess quantum physics too, right? Like it all touches on that.
Yeah, but as I said, it's like what is the most fascinating for me in this field is that it's never like one study or one approach that provides some very significant answer. It's usually a very complex interplay of different research groups working on something, on different people from different backgrounds. It's like a lot of small inputs about something, a lot of looking at the same problem from a lot of different perspectives, asking different questions, which are sometimes complementary. And then in the end, we kind of build a picture and try and manage to explain some phenomena which are in the world around us.
Very cool.
Have you ever run a simulation that completely challenged your assumptions?
It's usually the simulations that I was running had so many technical issues that it's not like you run a simulation, you ask a question, you run a simulation, you get the answer, and then you're mind blown how cool this answer is. It's mainly like the simulation fails, and then you have to figure out why did it fail. And then you kind of try to, figure out at what moment, because especially in the simulations that are multi-step, so you have to do one calculation, then the other, then the other, then there's a lot of research group, as I said, involved. And then when you put it in the end, you get the result, and then you try to analyze this result, and then it's usually trying to understand whether if it's meaningful physically, or was it some numerical artifact, or so I would say it's most of the work is actually trying to debug things or trying to understand what was some issue that didn't work well, that affected everything. So I'd say it's a quite challenging field, especially in some situations where it's not that easy to compare with experiment. Because when we talk about this particular field that I worked on, there is a lot of experiments. But the thing is that the conditions of the experiment and the theoretical model are quite different. And then there's all different theoretical models, but they all have different assumptions. And they are like, they're just not the same. They're always, there's always something which we cannot, if we compare them and we get the same result, we can be it's quite suspicious because we don't expect them to be the same. So in that sense, it could be quite challenging to sometimes, at least in my project, it could be quite challenging to understand if the model worked well or was there some numerical artifact or some instability. And then there is a lot of testing and a lot of changes and a lot of kind of, computational work just to try to see if the results are meaningful or not in the end.
Is there actually I'm sorry, go ahead, Frank.
No, I think it's all fascinating. It's all good. Sorry, Ken.
I was just curious, is there a quantum concept out there that still feels kind of mysterious or hard to wrap your head around?
Yeah, most of them. For me.
No, I mean, we laugh, but like that's important, right? You're obviously very accomplished. You're very smart, right? You just got your PhD. Congratulations, by the way.
Thank you.
If you find it hard, people who are regular civilians shouldn't feel bad about it being difficult. That's kind of, I see that as a positive, right? I see that as a positive sign.
I think it's if you think about it as a whole, it's complicated to everyone. I don't know if there is someone who can say, okay, I understand everything. Maybe there are people who are like more experienced and in these domains, but I would say it's so broad. And usually people tend to focus on something smaller. Like, as I said, like I worked on this specific project and I gained some expertise and knowledge on this specific project. But I would say the most important thing is just, as you mentioned, to be curious, because you will probably never understand everything. And especially if you decide to do research, you will work on the things that you don't know how to do because they just no one knows how to do them. And then in the end, of course, you will like learn along the way and you adapt, but one shouldn't be scared of not knowing things. It's completely normal. And also, it would be boring if you would know everything already, and
I was
what would
just
we
thinking that,
learn?
like, you're not going to do research in the stuff that people already know, right? Like, or that you already know, right? Like, it's one of those things where, by definition, it is by definition a
Mm-hmm.
you're not going to know. And even Richard Feynman, who is legendary, said, if you think you understand quantum mechanics, you don't understand the quantum mechanics, right? It is something that, until someone can explain all the weirdness, makes no logical sense to you know,
Mm-hmm.
our um to our world, right? Like, and that's an interesting question, right? So, you think about like the world humans occupy, right? Our day to day. Um, and there's things bigger than us, right? There's a fancy word for all these things. I forget what it was. But basically there's like planet-sized things, solar,
Mm-hmm.
galaxy-sized things, right? It's all underlying the same laws of physics, we think, right? But like those will behave differently than, me tossing a baseball, down the road or whatever. Um, um, and at the subatomic scale, like those rules are a little different too, right? Like it's a different game. And, our brains evolved to understand this level of reality, right? So it's kind of like things don't have to make sense for them to be true, is basically what I was trying to say.
Mm-hmm. Yeah, and I could say that's probably one of also the main problems in this domain is that we're kind of used to learning things intuitively, especially when it comes to physics. Everyone understands the forces because everyone was pushed at some point in their life. So we kind of can grasp these concepts without much of mathematics because we're just experiencing it in everyday life.
Right.
But when it comes to quantum, those laws are quite different. And then if people try to understand it intuitively, they could either misunderstand it or they could just get super confused, especially if you try to visualize something that's like it's just so difficult to visualize things. So and that's probably creating a lot of friction when people start to, like, let's just say, understand, get acquainted or learn this field, because it doesn't work as other sciences do when we can do things intuitively.
So is there something in nature, a smell, a color, a biological process, a flame, that makes you think this is quantum chemistry in action?
I think there is but then again, it's again, if we go on the very end of the process, when we perceive things, when the light hits the eye, I think in the very end there is a sort of isomerization of one molecule, and that, as far as I know, is one of the examples of quantum processes, which are kind of key process, or at least one of the key processes in the way that we can actually see the world around us.
Okay.
Very cool.
Could I
Um,
ask you? I'm sorry, go ahead.
oh, go ahead, Jens.
I'll say, if you could describe quantum chemistry using a metaphor from art or music or any metaphor, what would it be?
Quantum chemistry. That's an interesting question. Well, I mean, I would say quantum chemistry as such would be, I don't know how to explain the whole field, but let's say if we focus on perhaps if we focus on quantum dynamics, but I don't know. I mean, I would have to think about it a bit longer.
That's fair. Okay. Frank,
Yeah,
you
we don't
had
want to put you on
something?
the spot.
Yeah,
But
no,
I mean,
exactly.
I mean, there's so much. I mean, I can see why you would like this field, or anyone would like this field. Like, there's just so much to think about and so much to research, right?
Mm-hmm.
There's so many problems to solve, right? I mean, and this just seems so exciting. Quantum chemistry, quantum biology, like, Frank, I'm obsessed.
Oh
I
yeah,
just,
absolutely.
I just, there's just so many questions that I have that I want to understand. So, what's like a typical day for you, like when you're studying quantum chemistry, and What was a day look like for you?
Well, I would say the main problem in the domain was how to express the data efficiently, because these kind of simulations are usually one needs a huge amount of data. And we were working a lot with the tensor networks, with the tensor methods,
Really?
and trying to do kind of tensor decompositions and try to kind of compress the data. But then the problem is that when we compress the data, we also kind of lose the accuracy we might. So most of the typical day, it kind of depends on which stage of the project it was and what kind of the problem we are working on. But I would say the typical day would be trying to understand why something failed and how to make it work.
Interesting.
Hmm.
Interesting. No, it's all very fascinating. And tensors, right? So let's talk about that. Tensors are very popular in the AI field, which is what I do currently for my day job. They are also something that a lot of hardware companies are optimizing for. Uh, do you what do you know, when you're doing research or you're doing anything computational, do you use GPUs? Do you use kind of cloud, or is you focus more on kind of like the actual chemistry and the beakers and the pouring of stuff?
Well, I was using mainly the supercomputers. So
Okay.
it's in France, there are a couple of supercomputers which are kind of a different level. Some of them belong to university, some of them are national. So most of these kind of simulations are happening there. I didn't work with the GPUs myself, although there are also available. But in principle, for this kind of simulation, of course, one cannot run it on a local computer. So one needs to have some more computational infrastructure which can
Right.
support such kind of calculations.
Right. Not just a really good gamer PC card. Right? Like you need like one of those supercomputers. That's interesting. What's next for you? I see we're coming close to the top of the hour, so I want to be respectful of your time. What's next for you? Like, what are you doing now? You just got your PhD. You know, they used to be Candace. You remember these? Like you just won the Super Bowl. What are you gonna do next? I'm going to Disney
Exactly.
World.
I'm going to Disneyland, but yeah.
Yeah, that was
So
like these commercials. They stopped that about 15 years ago, so I
yeah.
don't know if anyone else remembers it. But so like, what's next for you? You just we're in the stadium, and I go to you and I say, you just got your PhD. What are you gonna do now?
Well, I put a lot of thought in what I want to do next, and in principle, I'm exploring the options in industry
Hmm.
because I kind of trying to decide what kind of research would I like to do, because I would like to still continue doing the research. And then there's this big question between research in industry and research in private in academia. What are the differences? What are the similarities? And I would say I kind of found that I would prefer to focus now on the more applied, although I wouldn't say more applied is a correct term, but let's say more of an application of a research to building something that can actually be tangible and that can, end up being some sort of a product and have some impact, which is more visible now and not a bit less visionary than it is in academia. So at the
Interesting.
moment, I'm exploring different options and following the trends which are currently what is going on in the research in private sector.
Very cool.
This has been absolutely fascinating. I'm really happy that we had you on as a guest.
And I'm
I
even
think
happier
that
that we recorded it this time.
no, we can't keep going back. That was a terrible mistake. So
Um, so
Thank you so much for inviting me. It was really
hey, no
nice to talk to
problem.
you
Where can
both.
folks find out more about you and what you're up to? Do you have a website? Do you have a LinkedIn or
I have
research
a
or
LinkedIn.
okay?
Yeah. I thought about creating a website, but I kind of never got around to do that. But I
Mhm.
would say the LinkedIn would be the best place if someone wants to connect or to just discuss a bit more about whatever science. That would be the best place, I would say.